Hi, good morning. Back again, CS61B Spring 2018 Midterm 1, Question 7, the downside of default. Consider the list of ints interface below. Add last get and size behave exactly as your deck interface from Project 1A. Sets the ith integer of list equal to value, plus equals adds each int in X to the corresponding int in list. So we'll just do like a pairwise type of addition. Then after the call is complete, L will contain values 7, 9, 11. If the lists are not the same length, plus equals should have no effect. So we're writing plus equals, taking in list of ints X. Oh, if the lists are the same length, they should have no effect. Seems like a good case for this if statement. So we have two objects here. We have ourself and the list of ints that's passed in. Assume X is not null. Okay. So if our size is not the same as the other size, then we're in trouble. So we should better quit early while we're ahead. Otherwise, for each int I equals 0, this is an interface problem. So let's see, interface problem. So I really only have access to these couple methods, right? Yeah, your gut instinct when you see this is like, you usually like to use the size method. Well, let's kind of think through our logic first. So we're gonna have to loop through the indices, and since they have the same size, we can just use I for both indexing myself and indexing X. But we do need to loop through all the indices, so it is going to be I needs to be less than the size. And since in this case we're not actually removing anything, it's okay to use a call to size and call size each time. Then we need to increment I, so we go through all the indices, and basically our strategy will be to loop through all the indices in the list, grab the item from myself, grab the item from X, add them together, and store them back into myself. So let me grab the item in myself, this dot get I. Oops, get I. And add it to what I get from X dot get I. Add it from my other person. Yep. And that should be a plus equals. Part B, the DL list of ints class is the implementation of list of ints. Oh, that stores a double list list of integers. So we're going to override the default plus equals method, fill in the plus equals method, so it's more efficient for linked lists. You must use iteration. Assume each list has a single sentinel node that points to itself when list is empty, like in Project 1A. Let's see. I think in this case, we're not assuming X is null, not null. X could be null. So since there's no statement, we might want to handle that case. So we probably want to maintain, of course, the same requirement in part A, that if lists are not the same length, plus equal should have no effect, as well as check for X is null. So this is actually important that we check X is not null first, or essentially if X is null, I always get scared about this, so I like to put parentheses. So if X is null, or if the sizes don't match, this dot size is not equal to X dot size. It's important that we check in this order, because if we check this dot size and X dot size before we do the null check, then the short circuiting won't work correctly. Because the reason why this works in the first place is that if X is null, it'll just say, oh, X is null, and it'll quit the if, and it'll say, okay, I already know this is going to evaluate to true, the entire Boolean context. And then in that case, we can just return and leave the program. So in this case, I will be very explicit and add the semicolon, just to say we don't need to do anything. Okay, so then the harder part is what to do inside this. Let's see, int node p equals sentinel.next. Okay, so it looks like we'll be starting from sentinel.next, looping down through the list until we finish. So one part's definitely going to be p equals p.next, so I can move down the list. Right, because that's the motion I want to think about. Then once I move down the list, when do I stop? I guess I should stop when I hit the sentinel. So if p is equal, stop when p is equal to, well, p is not equal to sentinel. Let's make sure our logic is correct. Well, p is not equal to sentinel. So to read this, it goes, let's start p at sentinel.next, while p does not loop back to the sentinel. So long as p has not looped back to the sentinel, p equals p.next. Okay. Let's see. I guess I'll somehow still need to be able to get the current item, right? I can certainly get the item from p. That's pretty easy. I can just say p.item. But how do I get the current x's item? Because x is a sentinel-based list. It's a little tricky. I think we'll probably need a similar setup with the int node here. Because you notice that the skeleton code gave us an int node that will be used as our pointer to traverse down through the hour list. We'll also need a pointer for x. So let's create an int node. Let's call x pointer xp equals the same setup. So it'll essentially be x dot sentinel dot next, just kind of going with the same pattern as the example that was given. And so this way we can keep track of the positions of both of them. Because without this int node x pointer, it would be very difficult to remember where you are in x, especially as you're iterating down and you're just kind of like, well, how many places do I need to go down? It's just hard. p.item, I think it should be okay to do plus equals xp.item. So that will plus together the first two, the first from each list. Then I need to move down xp. So xp equals xp.next. That will move the xp pointer down in space. Then the p pointer will also move. And then we'll keep on repeating this process until we compute the final result. And we're all happy.